Hi guys. So for notes today, we are going to be on page number 3. You're also going to want to have out your reference tables. We're going to be on page number 5 of your reference tables. Specifically, we're going to be using this table J activity series. So have that handy. I'm going to kind of be flipping between the two, as you'll see. So yeah, let's dive right in. So our next reaction type that we're going to talk about is a single replacement reaction. So sometimes also referred to as a single, let me move that up a little bit, a single displacement reaction. Honestly, it just kind of depends who you're talking to and what textbook you're reading. I have heard both. Again, the Regents tends to use the term single replacement, which is what we will typically be using, but they mean the same thing. So the general idea of a single replacement reaction is that you are going to have an element plus a compound giving you an element plus a compound. So you will notice what makes this different than like a synthesis reaction or a decomposition reaction. You have two reactants and two products. Okay, so that's one of the things to look at when you're trying to figure out what kind of reaction type you have. So it's usually between an ionic compound and an element. And the atoms of one element replace those of another in a compound. So metals will replace a metal, which is less reactive. Okay. So in other words, the more reactive element wants to be in the product. Let's see where I can squeeze this. I don't know. Any place I can squeeze this note. What if I just sort of move it? I don't know. Put that in someplace. Okay, the more reactive element wants to be in the product. So how are you going to know which is more reactive? We're going to use table J, where the top is the most reactive. And as you go down the table, it becomes less reactive. So if I flip over to table J real quick, you can see here's our metals. The most reactive or most active, whatever word you want to use, is at the top, and they become less reactive as you go down. Now, this is based on hydrogen. So you'll notice, even though we know hydrogen is not a metal, it's technically a nonmetal, hydrogen typically forms a positive ion. So in situations of reactivity, it acts like a metal, and everything is sort of compared to hydrogen, okay? So you can see H2 is right here. The only things less reactive than hydrogen would be copper, silver, and gold. And then everything more reactive than hydrogen is up above in order of reactivity, okay? So you have to think about single replacement reactions as being a competition, all right? Where the element by itself is going to attack the element in the compound. If the element by itself is more active than what it's trying to replace, it will kick it out and take its spot. So this example here, we have Mg plus ZnNO32. So Mg is our metal and zinc is our metal. Those are the two elements that are going to be in competition. So when I flip over to my table J, that's what I'm going to look for. I'm going to look for magnesium, which is right here, and zinc, which is right here. So what can we see? We can see that magnesium is higher than zinc on this, so magnesium is more reactive. So heading back, what that tells me is that the magnesium is going to come in, kick out the zinc, and take its place. So we wind up with MgNO32, and now zinc is by itself. Why? Magnesium is more reactive than zinc, so it replaces the zinc. So the general formula here, if we have AB, which is a compound, plus C, which is an element, and they tell us that A and C are both metals, but C is more active, more reactive, it's going to come in and kick out the A. It's going to come over, kick that out, and take its place. So my products here would be Cb plus A. Okay. Now, one thing I just want to mention, guys, when you're writing reactions, like in this example, I wrote this as having element plus compound. You can write it the other way and write it compound plus element. It means exactly the same thing. You know, think about math class. If I say 2 plus 3, that's the same thing as saying 3 plus 2. So on either side of the equation, you can reorder these and it doesn't change the meaning. So like for this second one here, if I had said Zn plus MgNO3, 2, it means exactly the same thing. You're allowed to swap your reactants and swap your products. You know what I mean? Like within a single side. Take a look at this next one down. It says we have Mg, that's my element by itself, plus LiNO3. So magnesium is a metal, so it's going to attack the metal in this compound, which is the lithium. So I head over to table J and I find those two elements. I find magnesium and I find lithium. And according to this, lithium is higher. So lithium is more active. So when I head back to my single replacements here, lithium is more reactive. It's already in the compound. So what happens? Nothing. No reaction. Why? Lithium is more active than magnesium, according to table J. Add that in there, just in case you're looking at this later, okay? All right, so let's take a look at this next one. We have Fe, that's my element, plus CuSO4. So Fe is a metal, Cu is a metal. Those are going to be in competition. I head to table J and I look for both of these. Eraser? Can I erase that? There we go. So I look for both of these. What did we have again? Iron and copper. Okay. So as I scroll through, here's my iron, Fe. Keep scrolling down, there's my copper. So what do I know? I know that iron is more reactive than copper. It's going to take its place. So as I head back here, Fe is going to come in, kick out the copper, and take its place. So I would have, what would that be? FeSO4 plus Cu. Okay. Now, one thing to keep in mind, in any reaction, when you make a new compound, so like in this example up here, I made the MgNO3 2. In this one here, I made the FeSO4. You always want to look up charges and cross and drop. So like going back to this MgNO3 2, how did I get that formula? Well, I took my magnesium, which has a +2 charge, and I combined it with nitrate, which is NO3, but that ion has a -1 charge. So when I cross and drop, that's how I wound up with MgNO3 2. If I take a look at this one here, so Fe, now Fe can have more than one charge. It can be a +2 or a +3. I just picked the +2 one since it didn't specify. That's combining with sulfate ion, which is SO4, which has a -2. So when you cross and drop and reduce, that's where I'm getting this FeSO4, okay? Now, what if your element by itself is not a metal? So like in this next one down, I have NaCl plus F2. So the element by itself here is fluorine, and fluorine is a nonmetal. Well, in that situation, it's going to attack the nonmetal in the compound, okay? So to fill in the notes here, nonmetals, meaning halogens, so chlorine, fluorine, bromine, iodine, will replace less active nonmetals. So if I head over to this table J, you can see I have my nonmetal side. So in this particular example, we are combining fluorine and chlorine. Now, as I look at my table, I can see that fluorine is more reactive than chlorine. Go. Fluorine is more reactive than chlorine, so it's going to come over and kick it out. Now, when I do this, I drop that little 2 subscript. So what I'm creating is Na is now with fluorine and Cl is by itself. Now think about charges here. Na gets a +1 charge. Fluorine gets a -1 charge. So do I need to add any subscripts? No, it's just NaF. Delete that out. Now what about the chlorine by itself? Can chlorine ever really be by itself? Because chlorine is one of our diatomic elements, those 7 special elements that can't exist alone. When they're in a compound with some other type of element, they're fine. But when you pull that chlorine out and make it be by itself, it's going to pair up. So this is actually going to be Cl2. Now you'll notice though, this reaction now is not balanced. So to balance this thing, I'm going to want to put a 2 in front of the NaF, and I'm going to want to put a 2 in front of the NaCl on the product side, or excuse me, on the reactant side. Okay. Let's take a look at this last one here. We have NaF plus Cl2, so we are in competition between the fluorine and the chlorine. As I go over to table J and compare those, I can see fluorine is more reactive. Well, fluorine is already in the compound, so what's going to happen? Nothing. No reaction, because fluorine, I'll just say F, is more active than Cl. Okay, so nothing happens. Now, in terms of halogen activity, so if you look at fluorine, chlorine, bromine, iodine, this is the exact same order they are in on your periodic table in group 17. So halogen activity decreases as you go down group 17, okay? So, ladies and gentlemen, I'm going to stop this video here. Nice and short, 11 minutes. Let me know if you have any questions at the end. In class, we will practice doing these single replacement reactions, okay? Have a great weekend, guys. Go Bills.